Hello everyone and welcome back to another video of CircuitDigest. In this video, I'll show you how you can build your very own smart fan speed controller like this one. Yes, this is just another home automation project, but this is very different from the ones that's available on the internet or even from the ones that we have built earlier. So as you know, many home automation projects uses a relay like this one to turn on or turn off a load, say for example your light bulb, your TV, your fridge, whatever it is. But the one that is less focused is on controlling the speed of the fan. So in this video, I'll show you how we can build a compact and a very practical circuit like this one, which you can use to control the speed of your fan. So this circuit differs from the others in two ways. One, it is a Triac based control, and two, it is very easy to install. So we'll have this complete circuit mounted inside this enclosure of ours, and we will even screw the terminals. So this is a ready-made enclosure. Even you can buy this off the shelf. You don't have to use a 3D printer for this one. And then what will happen is that you can just cut the wires which is going through the fan and insert one end of your wires, that is the live and neutral, over this side, and the live and neutral over this side, and the other end can go to your fan. So this is very easy to install. You don't have to create a mess on your regulator or your switchboard, and after you have installed, you can just put it into the cup holder of the fan and everything will look neat and tidy. So let me just quickly power on this device, connect a multimeter here, and show you how we are able to control the output voltage. Okay, here we are back again. I just have added a multimeter which is set into AC mode to measure the output AC voltage, and we have the system all powered up. So this is connected to the AC mains, which is 230 volts here in India, and I have just turned it on. And as you can see, the output voltage is currently 80, which is not good enough for a fan to turn on, meaning the fan will be in turn off state. Now what are we going to do is we're going to control the speed of the fan using the Blynk application. So I have just opened my Blynk application over here. So let me just increase the speed to 5, which is the maximum. As soon as I increase the speed, you can see that the voltage has increased to 215, which is the maximum mains voltage that I'm getting here. It should have been 220, but I'm just getting 215 from the AC outlet itself. And you could have also heard the buzzer beep, meaning that the ESP picked the command that we sent it. Just let me reduce the fan speed, and you can see it is 150 volts. And if I go all the way down, it goes to 80 volts, which is for the minimum speed of the fan. So let me just quickly show you again. So it will be 137 if I set it at 20, and if I go all the way up, the voltage increases to 215. So this is just a simple demonstration. Stay tuned, for I will be showing how the entire circuit works, and at the end of the video I will also mount this to a real fan and show you how it can be controlled from your Blynk application. So let's get started. So as I told you, in this video I'll explain the complete circuitry of this project, and I will also show you how we fabricated this board. But before we get there, it is important for me to mention the sponsors for this video, PCB Way. PCB Way provides high quality and cost effective PCB prototype and fabrication services. They are well equipped to handle standard and advanced PCB designs and can also provide assembly stencil and PCB assembly services. They are known for their shorter lead time and customer service, and also supports the maker community. So do consider giving them a try for your next PCB. Now let's take a detailed look of the circuit diagram for our project. I have just removed the AC mains wire so that we can have the board clearly for explanation. So this will be the complete circuit diagram of the project that we are going to build, and this will be our final outcome. So let us start from the input side of the project. Now the input is of course 230 volt AC mains. It depends on where you live. In India it's 230 volt AC mains. So we are going to take this AC mains and we are going to use an AC to DC converter module from Blynk to get 5 volts. So we have just used an EMI choke to filter out all the common mode noise, and then we have used the Blynk AC to DC converter, which you can see here. So this module here can take input from 100 volts to 240 volts AC and can give you 5 volts DC with a maximum current of 1 amps, which is more than enough for a project. Now, even if you're living in other countries where your operating voltage is 110 volts, you can still use the same circuit because this module here can operate from 100 volts to 240 volts AC input. Now, once we have our 5 volts, we have just used two filter capacitors to remove any noise which might come from the switching module, and then we have used the AMS 1117 as you can see here. So the AMS 1117 is used to convert the 5 volts from this module to 3.3 volts because we will be needing 3.3 volts for our ESP chip, and we'll be needing 5 volts for these op amps and Triac control circuitry and extra. So you can see that we have our 5 volt output here and 3.3 volt output here. Again, we have used two filter capacitors to filter out any noise that we might get. Now, taking a look at the board, you can see that most of the through hole components are placed on the bottom surface, on the top surface. You won't be able to find the AMS 1117 here. To find that, you have to turn the board around. You can see that we have our AMS 1117 IC over here. Let me just zoom in, so I think you can see a better view of the board now. So please pardon me for all these glow sticks because I need the wire to be held securely. I should have shown this board before doing the hot glue work, but I believe you will still be able to look at the IC over here, which is AMS 1117. Now, going back to the circuit diagram, now we have a 5 volt and 3.3 volts ready. The next section is about the zero cross detection, which you can find over here. So this is the zero cross detection circuitry. So basically, as we know, we are going to do phase angle control on the sine wave. A typical sine wave looks like this, and we have to start our phase angle control from the zero crossing point. Now, this is not mandatory. You can also do phase angle control without zero cross detection, but you will get a humming noise on your fan if you don't do zero cross detection. So this circuitry over here uses the PC817, which you can find over here. PC817 is over here, which is an optocoupler. This is used to find when the sine wave is crossing zero. So how it works is that we have a diode bridge rectifier. So as we know, a diode bridge converts the positive half cycle and the negative half cycle to a pure DC wave. So whenever this sine wave touches the zero, the bridge rectifier will not have anything to provide. It will neither have a positive cycle nor have a negative cycle. So for that brief moment, this PC817 will be triggered, and since the output is latched to ground, whenever there is no voltage provided on the input side, we will get a small pulse on the output. And when do we have no voltage on the input side? Whenever the AC voltage is zero, there won't be any voltage provided to our optocoupler. So this outside point will be triggered, and there will be a small pulse whenever the sine wave touches zero over here. So this pulse is then provided to our ESP12 or the ESP node MCU controller. We'll get back to it later. We just have provided a label here. We'll be using this to trigger the Triac to control the phase angle of our input sine wave. Now our next section would be the Triac section. So this is the Triac and its optocoupler section. So what we have used here is another optocoupler called MOC3021, which you can find on the board over here. So the reason for using two optocouplers is that one is used to detect the zero crossing section and the other is used to control the Triac. Now, whenever you're working with AC and DC, you will find a lot of optocouplers because these are used for providing isolation. If you see, this is the AC side and this is the DC side. So optocoupler acts as an isolation. So this complete side is DC and this is going to the controller, and the same thing is applied over here. So this is our AC side over here, which is being triggered by the Triac, and this is our DC side, and the optocoupler in between is used to provide isolation between both the sides. So now what happens is that we are using this optocoupler to drive this particular Triac. Now please ignore me for the symbol over here. The symbol shows an SCR, but it is actually a Triac, which is BT136, which you can see over here. The Triac is placed on a board over here, and you can see that we have controlled this optocoupler through the PWM signal. This PWM signal will be given from our node MCU, and we have BC847 transistor to switch this optocoupler. Now based on the PWM signal we are giving here, the optocoupler will control the Triac, that is, it will turn on or turn off the Triac to reduce or increase the phase angle of a sine wave, thus controlling the output voltage. Now another interesting thing is that we have to use a Triac here because Triacs are the only switches which are bidirectional, that is, we have to conduct both in the negative and the positive half cycle. And then another important part here is the snubber circuit, which is an RC snubber, which we have done using the resistor R12 and C13. Now I have done some rework on my PCB because initially I thought I could use an SMD resistor for the snubber, but that turned out wrong. So I had to use a through hole. So that's why you see these components don't have a proper placing. But don't worry, I have updated the Gerber. The one that you will find at the link given in the description will have the updated Gerber files. Now the importance of this snubber circuit is to remove any back current which might flow from the inductive load. Now as we know, fan is a motor, and motor is made of coils, and coils are inductors. So whenever we are switching a coil, there will be a lot of back EMF or back current, and this snubber circuit is used to protect our Triac from that back EMF. And then moving on, other sections are not power electronics related, they are purely embedded related circuits, so it is pretty much simple. Now we have used the ESP8266 chip directly on board. As you can see here, the chip is directly on board, and this is done because I have to save space as much as possible. The complete node MCU board would have occupied a lot of space, so these setups are the mandatory connections to make the ESP work. So what we have done is that, as you can see, we have the IO0 and IO2, which is over here. IO0, IO2 is pulled high to 3.3 volts, and IO15 is also pulled to ground using this resistor of 12K, and all this is mandatory to make your ESP12E work. And then on the casing, you can see that we have provided two buttons. Let me just zoom in. So when we finally mount this board, you will have access to these programming pins over here. So you have to press the boot and reset button to program your ESP12. But once you have done the programming, you won't have to access these two buttons anymore. We have just pulled out these pins for, like for easy programming and debugging of this module. Now coming back to the circuit diagram, here we have just made connections for the reset button. The reset pin of the controller should be pulled high to 3.3 volts, and over here we just have our buzzer circuitry. So we have used a GPIO pin of the ESP12E for a buzzer which is connected here. The programming pins RX and TX is connected to the output pin which I showed you earlier. We have our programming pins over here, ground, 3.3 volt, TX and RX, which I just showed over here. So that's it. So all these are the embedded related section which we need to program the ESP12E and also monitor the serial output. So that is it. The circuit diagram is pretty simple. Hope I have covered everything. Let me just quickly come again to this switching section. I think I missed one point. So as I mentioned earlier, we have our AC here, which is line and neutral, and as I told you earlier, you can see that this line is taken to the Triac over here, and then we switch it and we provide that line as line out. So this line, this AC line you see here is a pure 220 volts AC, that is in my case India, and the output you get here is switched, that is phase angle controlled, and the phase angle depends on the PWM you give here, and this output is provided to the output screw terminal, which you can see in the board over here. So this is our output. So yes, so this is our switched output. So this line out is the switched line, and the neutral is coming from the AC main. So you can see the neutral from here is coming all the way to here without any changes. So that is it, guys. The circuit is very simple. It might sound a bit complicated, but as I told you, it is very easy to build one on your own. Now all these glue that you see here is just used to keep the components in place. You can add a heatsink to the Triac if you need, but other than that, this board works just fine. So now once your circuit diagram is ready, since this is an AC circuit, you definitely have to either solder it on a perf board or get a PCB manufactured. So as I told you earlier, this video is sponsored by PCB Way, and we got these PCBs manufactured from PCB Way. So let me just quickly show you how to get your own PCBs from PCBWay.com. To order your PCBs from PCB Way, just get into their website PCBWay.com, and you will be greeted with their homepage something like this. Then make sure you're already signed in, as I am signed in already. I'm just going to proceed with entering the dimensions of my PCB. In my case, for this ultrasonic sensor based digital ruler, the dimension of the PCB is 60 mm cross 60 mm, and the number of PCBs I need will be 5 pieces, and it is a 2-layer PCB with 1.6 mm thickness. Now when you click on quote now, you will be taken to another page where you can feed in few more details about your PCB if required. But in our case, we don't need to change anything. If you're curious to have PCBs in other colors, you can change the color here. The best thing about PCB Way is that irrespective of what color solder mask you choose, the pricing is going to be the same. So you can choose any color solder mask you want. After that, on the right side, you can see the total amount of cost you have to pay for the PCB. In this case, it will be India. And I'll be choosing the postal shipping because it is the cheapest. Now after I have chosen my country and the mode of shipping, I'll be able to see the final rupees that I have to pay to get my PCBs fabricated, and it will also tell me when the PCBs will be shipped and when it will be received. Very handy if you're in a tight timeline. So once you're sure about your PCB cost and the delivery date, just click on save to cart, and you'll be taken to another page which lets you to upload the Gerber file. Now over here you can just click on add Gerber file and upload the Gerber file which you generated using your PCB software. If you need the Gerber file for this project, again it can be found at the link given in the description. Once you upload the Gerber file, just click on submit order now, and the PCB Way will take around 5 to 10 minutes to complete the review, and after that your PCBs will be fabricated and it will be sent right to your doorstep. So within few days of ordering the PCB, I got them delivered in a neatly packaged box like this one, and as you can see, the quality of these PCBs are also really good. Now you can see a lot of cuts on this board because I have provided isolation between the analog and the digital side, sorry, the AC and the DC side, between the phase and the neutral, wherever the tracks are getting close, we have used a cut. And you can also see that we have made impedance matching for the RX and TX line. So apart from that, the board is pretty simple in terms of design. We have tried to place all the SMDs on the back side and all the through holes on the front. So as you can see, the board quality is really good. The tracks, the bias, the pads, everything was neatly fabricated. So once you got the board, you can just directly proceed with assembling the components. And my board looks something like this after I have soldered all the components on top of it. As you can see, we have a small high voltage warning over here, and this entire thing was planned for a heatsink, but I have not used a heatsink as of now. And another thing was, this board was planned for this particular casing, which you can get off the shelf. It's a ready-made casing, mostly used for tube-like chokes, I guess, but in this project we'll be using it for our smart IoT fan controller. Now it is written EC80 inside this casing. Maybe you can use that number to get the same casing on your own. So as I told you, the PCB was designed for this casing. As you can see, if I mount it inside, you can see the holes get aligned perfectly to the corner. So you can just keep the board inside, cover it, and use your screws to mount the casing, and tada, you have your own smart IoT based fan controller, which you can directly mount to your fan and start controlling your devices. The wires will go through these holes over here, and you can connect it to your fan, put it into the casing and test it out. And I'm going to do exactly that. So let me just pause the video here, mount it to my fan and show you how the entire thing works. So here we are back again. As I told you, I'm going to demonstrate it with this fan over here. We have already installed our device. If you can see, it's on the back side of the fan. Let me check if I can zoom in for you. So yes, so as you can see, our device, which I just demonstrated to you, it's installed over there. If you want to know how to install, and if you want to see some pictures of installation, you can again check the article linked at the description of this video. So now let me show you how it is working. Now as you can see, the fan is already running in medium speed because I asked it to. Now I'm just gonna open my app. I hope you can see it. As you can see, we just asked that to run in medium speed. Now let me just turn it off to the lowest speed possible. You should have heard 2 click sounds, meaning our ESP has registered that call. I'm sorry, you're not able to see the phone properly. Now as you can see, the speed is set to 0 and the fan is in complete still. Let me set it to medium speed. You can hear that the ESP gave a beep, meaning that it recognized our command and the fan has started to work in medium speed. Now let me go to full speed again. And this is the full speed. So that is it, guys. This is how the project works. Hope you enjoyed the video. Let me just slow down the fan. Now I have turned it off completely, and as you can see, the fan comes to a complete still. So that is it. This is how you can build your own IoT based smart fan. Hope you enjoyed the project. If yes, give us a like, and also comment if you want to see more interesting IoT projects on this channel. Now you can even make this project further more interesting. You can add a DHT11 sensor over there. Instead of controlling it from fan, you can program a Node MCU or an Arduino to control the speed of the fan based on the temperature in the room. Now I have demonstrated using a wall mount fan because I don't have a ceiling fan in my office, but it would work the same for any other fans. So that is it, guys. Thank you. Have a nice day. Bye bye. This is Ashwin signing off.